Hello, good morning. Am I audible?
Yes, sir.
Okay, good morning and welcome to a lecture on advanced power electronics. Yesterday we start with a two-level inverter. Our conventional bridge inverter, whatever shown is figure, this will be a two-level inverter. Last time we discussed the concept of pole voltage. For that, we divide the DC voltage equal DC voltage, and center point of this DC voltage is called as O. And with respect to this point, we measure the VAO, VBO, and VCO. And these voltages we can call as a pole voltage or the node voltage. And these voltages, when let us assume when S1 is on, our VAO will be a plus VDC by 2 because point A is connected to upper this. So VAO will be plus VDC by 2 when S1 is switched on. Whereas when S4 is switched on, this point A will come to the negative of this and our VAO will be a minus VDC by 2. So VAO or VBO or VCO, these pole voltages has only a two values, either plus VDC by 2 or minus VDC by 2. That's why this inverter we can call as a two-level inverter. So VAO, VBO, VCO, these voltages has either a plus VDC by 2 when upper switch is on and minus VDC by 2 when lower switch is on. That is why this level, this inverter, we can call as a two-level inverter. After that, we have shown the switching states of the inverter. What are possible switching states? We represent when one, so here MSB and last is LSB. So 1 1 1, it means one means first MSB one means upper switch S1 is on, then middle one means S3 is on, and LSB one means S5 is on. So 1 1 1, it represents upper three switches are on. Similarly, 0 0 0 0 means a lower switch is on. So 0 0 0 means S4, S6, and S2 on. Similarly, we are having 1 0 1. 1 means S1 is on. Middle 0 means S6 is on. And LSB1 means S5 is on. So 1 0 1, it means that S1, S6, and S5 are on. So this inverter, we are having 8 switching states. If you just, we have listed it here, a possible switching states will be a 8. That is a 2 raised to 3. We are having the switching states of the inverter. Now let us go for, we are going for the concept of voltage space vector. We are going the concept of voltage space vector. So here, a representation of three-phase quantity, may be sinusoidal, may be non-sinusoidal. Which three-phase quantities? May be voltage, may be current, may be flux linkages. These quantities can be represented in a two-dimensional space. Everybody knows X, Y. This is our two-dimensional space, and a three-phase quantity, which may be a DC, which may be a sinusoidal, which may be non-sinusoidal. Any quantity we can represent with a space vector. For voltages, it is a voltage space vector. For currents, it is a current space vector. For flux linkages, it is a flux space vector, and so on. While doing this, we are just having the three axes. These are the three axes, not the phasors. Very clearly, what we want to say is A, B, C. A, B, C. These are the axes, three axes, and they are fixed in two-dimensional space. They are not phasors. Phasors are rotating. They are not. They are having just the XY coordinate axis. Similarly, it's the three axes which are separated by 120 degrees apart, which are separated by one. They are not moving. They are not moving. They are fixed in the a particular two-dimensional space. And quantity along them, along A we are having one voltage, maybe a VA, it may be VB, VC. Along these we are having a three voltages. They may be sinusoidal, they may be a 120 degrees phase shifted, they may not be a 120 degrees phase shifted, they may be a DC quantities. So here along these three axes we are having a three quantities, maybe a voltage, so VA, VB, VC, or we are having IA, IB, IC. Then these resulting three voltages can be represented by one equivalent voltage. So resulting these three in the three, particularly we are seeing we are having a three phase voltages. So these three phase voltages which are having a, okay, they are varying sinusoidally or may not be varying sinusoidally. A phase voltage VA is on along A axis, VB is along B axis, and BC is along C axis. Here they are varying with respect to time. They are varying with respect to time. They may be phase shifted, they may not be phase shifted. And these three quantities or three voltages can be represented with the equivalent one voltage vector, equivalent one voltage vector in the two-dimensional space. One voltage vector. It may be a stationary, it may be a rotating at constant speed, it may be a rotating at non-uniform speed. So our intention is space vector is nothing but sorry, a space vector is nothing but representation of these three phase quantity in a one vector, and this vector may be a stationary, may be rotating, its amplitude may be constant or may be a changing. Now we can go for just how to obtain the a space vector. So we have just discussed what is mean by the space vector. Now let us VA, that is voltage along A phase voltage, that is Vm sin omega t, and this voltage is along the A axis. Let us assume that the sinusoidal voltage along A axis. Then along B axis we are having a second phase voltage Vm sin of omega t minus 120 degrees, and third case VC Vm sin omega t plus 120 degrees. So these are three. Here we consider three sinusoidal and balanced voltages. So here we consider three sinusoidal and the balanced voltages. And when they are sinusoidal and balanced voltages, then we see that instantaneous addition of the three voltages, three phase voltages, that VA, VB, and VC. Instantaneous addition of these three voltages will be a zero. And these three voltages we can represent it in a two-dimensional space like this, one vector rotating in the space. It can be represented a two-dimensional vector in space. It may be stationary, it may be rotating depending upon the what here. We can now go for this. Now how we define the space vector? So here we can go for whatever this VA is along A axis, VP is along B axis, and BC is along C axis, and we can write a space vector here, VA plus VB e raised to j 2 pi by 3 plus VC e raised to minus j 2 pi by 3. So that will be our expression for how to obtain the space vector. Okay, and we put a VA equal to Vm sin omega t, VB equal to Vm sin omega t minus 2 pi by 3 or minus 120. Similarly, VC Vm sin omega t plus 120 degrees. And now here we substitute these values, and e raised to j theta we use the formula, okay, cos theta minus j sin theta, e raised to theta formula we can use it, and then this you can get into the rectangular form, and from rectangular form you make the summation, and you get a one vector. That will be, if you simplify this, putting Va equal to Vm sin omega t, Vb equal to Vm sin omega t minus 120, and Vc equal to Vm sin omega t plus 120 degrees. And e raised to j theta formula you can use, cos theta plus j sin theta you can use it, and putting the values, ultimately you will get the Vs, that is the resultant voltage. This is three phase voltages, and resultant voltage 3 by 2 Vm sin omega t minus j cos omega t. Okay, and here this is represented in the a polar form, sorry, rectangular form. It is a rectangular form, and if you get the polar form, we'll get a constant magnitude of Vs, that will be equal to 3 by 2 Vm, and it rotates at a omega radians per second. It rotates at the omega radians per second. So here what, when our three phase voltages are balanced and sinusoidal, here when our three phase voltages are balanced and sinusoidal, then what space vector we can obtain? Voltage space vector. A voltage space vector is of constant magnitude, and it rotates at a uniform speed. It rotates at a uniform speed, and the speed is the omega. So is it clear? Any question regarding this? What is the voltage space vector for three phase balanced sinusoidal voltages? What is the space vector, voltage space vector for three phase balanced sinusoidal voltage? Any doubt?
No, sir.
Uh, so what is our, when we are having a three phase voltages are sinusoidal and balanced, then our, what is the voltage space vector? What is voltage space vector when we are having a three phase balanced sinusoidal voltages? A space vector is having, is the magnitude of space vector changing?
No, sir.
Magnitude remains fixed. What is amplitude? Its amplitude is 3 by 2 1.5 Vm. What is meaning of Vm? Vm is the peak value of phase voltage. Vm is the peak amplitude of phase voltage. So space vector, whatever this space vector is a, whatever the space vector, it is having a constant amplitude, and it rotates at omega radians per second. So at a speed of this will be a omega radians per second. Or in one cycle of our AC supply, one cycle of AC supply, here in one cycle of AC supply, it will complete one rotation. One cycle of supply voltage, one cycle time, a supply voltage, it completes the one rotation. For 50 hertz, how much is the time required for voltage space vector to complete one cycle, one rotation? How much time is required for a voltage space vector to complete one rotation when input supply is a 50 hertz? How
20
much time?
milliseconds.
How much time is required for a voltage space vector to complete one rotation?
20
It will be
milliseconds.
20 millisecond. It will be a 20 millisecond. One cycle time is required to complete the one rotation. Now let us go for, now last time we have discussed the phase volt pole voltages. Is it right? So with this concept, okay, we have just put up the concept of voltage space vector, and what is conclusion regarding a three phase balanced voltages, sinusoidal balanced voltages. Our space vector is having a constant amplitude, and that constant amplitude is 3 by 2 Vm, where Vm is the peak value of a phase voltage, and it rotates at omega radians per second, or it requires one cycle time to complete one rotation. For 50 hertz supply, our space vector will take a 20 millisecond to complete one cycle. With this, now we can go for the relationship between the pole voltage and the phase voltage. Now pole voltage is fixed. Either it will be plus VDC by 2 or minus VDC by 2, depending upon upper switch is on or the lower switch is on. Now let us take here, we have connected. So this is the inverter, same diagram we have taken. This is a neutral point. We have connected a star connected load, assume it RL load or a resistive load here. We have made a star, and this is our neutral point. Let us assume that this is the neutral point, and this is our, so we are having a OA, OB, OC. So whatever OA, OB and OC, these are pole voltages. Whereas AN, PN and CN, AN, PN and CN, these are the phase voltages. These are the phase voltages. Now let us assume that how we represent the VAO. How we represent the VAO. So VAO, okay, this VAO will be a VAN, okay, VAN plus VNO. Okay, so we write it VAO. VAO here will be a V, here AN, VAN, VAN plus VNO, VNO. Is it clear? So VAO, that is AO is the pole voltage, it will be VAN plus one voltage between N and O. Okay, we write it here. So we write the expression for VAO. Similarly, we can write the expression for VBO. VBO is the VBN plus VNO. VBO will be VBN plus VNO. So we get a VBO. Similarly, we write the VCO. VCO will be equal to VCN plus VNO. So this we are obtaining the three voltage relationship. So VAO, VBO, VAO. We add all three. We add all these three. We get an addition of all these three. We add the three voltages. We add the three voltages. So your addition will be VAO plus VBO plus VCO. We added together. We added VAN plus VBN plus VCN. So addition of this VAN plus VBN plus VCN. What we get? Addition of VAN plus VBN plus VCN will be equal to how much?
Zero.
Addition of three phase voltages will be equal to, instantaneous addition of three voltages will be equal to 0. Will be equal to 0. So this we are having a 0. Okay. So and NO plus NO plus NO. So this 0 we represented here. NO plus NO plus NO, 3NO, and that will be equal to VAO plus VBO plus VCO. So this is our expression. We get addition of these three voltages. When we add the three voltages, we'll get the thrice VNO, and this VAN plus VBN plus VCN will be 0, and VAO plus VBO plus VCO. And now we get a VNO from this. VNO will be a 1/3, 3 will come this side. So VNO will be 1/3 of VAO plus VBO plus VCO. That is NO voltage. We are obtained this. And now our job is NO, we put it here. Each equation, we put the value of NO. So here, this NO, you can put it here. Whatever this VAO will be AN plus NO, and this NO will be 1/3 VAO plus VBO plus VCO. And here 1/3 plus this 1. Okay, so here 1/3 VAO plus VAO. How much will get? 1/3 plus VAO plus. So here we get a VAN will be equal to this, and then VN, sorry, VAN we want to find out. Okay, VAN will be, now expression will be VAO minus VNO. VAN will be equal to VAO minus VNO, and NO we will put it here. So VAN will be VAO minus one third of VAO plus VBO plus VCO. So this will be 1 minus one third. So this will be two third. So our expression for AN, we are getting the expression for AN. What we have to do? So here VNO, we put the value of this value we can put it here, and an will be equal to vao minus vno, and this minus vao minus vno, just simplify this, we get van, that is phase voltage. Van will be two-third vao minus one-third vbo minus one-third vc. So here we are having a vao as a fixed value. What is value of vao, vbo, vco? What is the value of here VAO, VBO, VCO? What are the possible values of VAO, VBO, VCO? Am I audible? What is
Yes, sir.
value of VAO, VBO, VCO? For a two-level inverter, we are going for a two-level inverter. VAO is what? A pole voltage. VBO is the second pole voltage, and VCO is the third pole voltage. So what is
Plus
the
minus
magnitudes
VDC
of
by 2.
VAO, VBO, VCO?
Plus or
Anything?
minus VDC by 2.
Minus VDC by 2 or
Plus VDC by 2.
plus VDC by 2, depending upon which switches are on. At one instant, how many switches will be on? At one instant, how many switches will be on from this inverter? At any one, take a one instant of time, how many switches will be on?
2.
So here we are don't have either upper switch should be on or the lower switch should be on. Okay, we don't have a both switches are off. Is it right? So either one switch is on from one leg, the second leg one switch is on, third leg one switch is on. So what is a at one time how many switches will be on? At one instant, how many switches will be on in a two-level inverter? Hello, am I audible? How many switches will be on at one instant in a three-phase two-level inverter?
Any two switches which are not from the same leg.
No, no, no. I am once again I am telling, from each leg one switch is on. From each leg, one switch is on. Is it right? So how many switches will be on simultaneously?
3.
How many switches will be on simultaneously?
3.
Three switches will be on. And depending upon three switches, VAO, value of VAO either plus VDC by 2 when S1 is on, and VBO will be a minus VDC by 2 when lower switch is on of that. Means S4 is on, our VAO is minus VDC by 2. Similarly, VBO will be a plus VDC by 2 when VBO is plus VDC by 2 when which switch is on? VBO is plus VDC by 2 when which switch is on? VBO will be plus VDC by 2 when which switch is on? When upper switch is on, what is our voltage? Plus VDC. Lower switch is on, minus VDC by 2. Sorry, upper switch is on plus VDC by 2. Lower switch is on, minus VDC by 2. So for VBO is a plus VDC by 2. So which switch will be on?
S3.
S3 will be on when VBO is plus VDC by 2. S6 will be on when VBO will be a minus VDC by 2. Similarly, VCO is plus VDC by 2 when VCO is plus VDC by 2 when S5 is on, and minus VDC by 2 when S2 is on. Is it clear? So this here VBO, VCO, VAO, they are only two specific values, not other value. What these two values? Either plus VDC by 2 or minus VDC by 2 depending upon the which switch is on. Upper switch is on plus VDC by 2, lower switch is on minus VDC by 2. So is it clear? We write the expression for VAN, phase to neutral voltage. Similarly, from this, we want to VBN will be equal to VBO minus VNO. And we put this VNO, VBO minus VNO, put the value of VNO, one third of VAO plus VBO plus, just simplify this. We'll get the expression for VBN, two-third VBO minus one-third VAO minus one-third VCO. Okay. Similarly, we put a value of VNO in the VCO minus VNO will be VCN. Putting the value of this VNO, we get the expression for VCN. And these three equations we represent in the matrix form. VAN, VBN, VCN. We take a one-third common, then we get the matrix is simple matrix 2 minus 1 minus 1 minus 1 2 minus 1 minus 1 minus 1 2. Diagonal elements are 2, other elements are minus 1. Diagonal elements are, it is 3 by 3 matrix. Diagonal elements are 2, other elements are 1, and we are multiplying by one third. And here we just discuss VAN. What is VAO? VAO has only two specific values. VAO has only two specific values, either plus VDC by 2 or minus VDC by 2. Similarly, VBO has only two specific values, plus VDC by 2 or minus VDC by 2, similar VCO. And once you know the switching state, is it now my question is, how many switching state for two-level inverter? How many switching states for two-level inverter? Am I audible? How many switching states for two-level inverter?
6.
Okay, again we can go back. We are having a two-level inverter. We have shown the switching states. So how many switching states for two-level inverter?
8.
8. So we are having the switching states of the inverter, two-level inverter are 8. Okay. So for each state, is it possible to find out the VAN, VBN, CN? Yes or no? For each state, how many switching state for the inverter? Two-level inverter, how many switching state? Two-level inverter are 8 switching states, and for each switching state, we can find out VAN, VBN, and VCN. Is it okay? Once again, I will repeat. How many switching states for two-level inverter? We are having 8 switching states for a two-level inverter. And for each switching state, we are having a specific value of VAO, either plus VDC by 2, minus VDC by 2, similar case for this. And putting these values, will get the phase voltages for all switching states. Phase voltages for all the 8 switching states. Is it clear? Now, let us go for. So here we have just procedure to obtain the voltage space vector. Okay, now how to obtain the voltage space vector? So we have studied these three, is it right? First we obtain the values of VAO, VBO, VCO. Is it clear? How to obtain the VAO, VBO, VCO? Depending upon the switching state, values of VAO, VBO, VCO will be plus VDC by 2 or minus VDC by 2. And once you know the VAO, depending upon which switching state, we take one particular switching state, and for that switching state, you put a VAO, VBO, and VC. Once you put these values, you just compute it, and you will get the VAN, VBN, and VCN. Now, once you get these values, VAN, VBN, VCN, now we have to this. Let us assume that these values, I will just write it here. Let us on this x-axis, a-axis, we are having what value? Let us assume that we are having a value is VAN. Along a-axis, which value we are having is AAN. Okay, this is our AN value along the a-axis. Along the B axis, we are having which value? Along the B axis, we are having a VBN. Okay, this is our VBN. We are having VBN along the uh, B axis, and VCN BCN along this C axis. VCN will be along this C axis. Is it right? We are having these three voltages VAN at a particular, they are having constant value at a particular switching state. Our as a VAO, VBO, CO are the constant. Is it right? These values are constant, either plus VDC or one constant values here. All three values are constant, and hence these values are a constant. Here VN we get some specific value, VBN will get a specific value, VCN will get a specific value. And we have to resolve these three voltages along the x-axis. We resolve along the particularly x-axis. So x-axis will be this. Along the x-axis we resolve, and along y-axis we resolve this. Okay, so these quantities we can resolve, and summation of all these quantities along the x-axis. So what we'll be having, we are having VAN as it is along the x-axis, and B we can just project on this along the y-axis. This angle is how much now? 30. Is it right? This 30 degrees, and this along y-axis is a positive. We are in cos 30. Sorry, so BN we are having. Okay, sorry. We have to resolve along. Sorry, I have to make a mistake here. We have to resolve all along the x-axis, and here we get this. Okay, and here we have seen that we are getting here. We project this B along the x-axis. Okay, B along this x-axis, and this is the magnitude what we are interested. And now this angle will be a 30. Okay, this angle will be a 30. So sine 30. So this is a 0.5 VBN, and it is opposite direction. So this will be a minus 0.5. We can get it BN. Similarly, the CN we can resolve here. Whatever CN value we resolve, again it will be, this angle will be a 30 degrees. This angle will be a 30 degrees, and so cos of, sorry, sine of 30 will be again a 0.5 negative direction. So we resolve this along three components along the x-axis. This is the AN as it is. A component of CN along x-axis is this. So we resolve the components AN, VAN, VBN along the x-axis. As VAN is along x-axis as it is, its value will 1. This is a VBN. This is a VBN. We resolve along x-axis, and its value will be 0.5, which is, and this angle is 30, sine of 30, 0.5, and it is opposite minus direction, so it is minus 0.5 BN. And CN we resolve along the x-axis. Again this angle is 30, so sine 30 will be a 0.5. So this is we resolve 3 along x, and resultant is the Vx. Resultant is the Vx. Similarly, we resolve all along the B, whereas here component of AN along B is 0, because AN is along A axis. So along y axis, sorry, along y axis our value of VAN is 0. So we taken a VAN is 0. Now this B we resolve along y axis, and it will be cos of 30, a positive value, and so it will be plus 0.866. Similarly, VCN we resolve along the y-axis. It will be here, and again a cos of 30. It will be minus, because it is opposite direction, minus 0.866 CN. So here, once we know the values of VAN, VBN, VCN, once we know the values of VAN, VBN, VCN, we find out Vx, a total quantity along x-axis, and total quantity along y-axis. And once you get a total quantity along x-axis is Vx, Total quantity on y-axis is Vy. And then resultant of these two will be a square root of Vx square plus Vy square. Square root of Vx square plus Vy square will get the magnitude. And this is the magnitude of voltage space vector. And this theta, we take a tan theta. So we can take a tan theta, that is our Vy front side divided by adjacent side. So the theta will be a tan inverse of Vy by Vx. So we find out the magnitude of space vector and we find out theta. Depending upon which value, our Vx may be a positive, Vy may be a positive, both are positive, we'll get the space vector in first quadrant. If Vx is negative and Vy is positive, we'll get second quadrant. So angle will be a second quadrant. If both are negative, Vx is negative, Vy is negative, we get the angle in third quadrant. Vx is positive and Vy is negative, we get the angle in fourth quadrant. So theta may be, what are the possible values of theta? Theta may be any value between 0 to, what is the range of theta value? Theta, that is a space vector makes angle with respect to horizontal axis. That theta, a range of theta may be from, what is the range of theta? It may be
0 to
any
pi.
sector. It may be any quadrant. It may be first, second, third, depending upon which value is positive. Both Vx, Vy positive, angle may be 0 to 90. If Vy is positive and Vx is negative, it may be 90 to 180. Both Vx and Vy are negative, 90 to 270. Okay, and here Vx is positive but Vy is negative, it will be 270 to 360. So the angle theta may be varying from 0 to 360. Any value depending upon the values of VAN, VBN, VCN. And values of VAN, VBN, CN will depend upon what is the switching state. So here for each switching state, we can find out a magnitude of space vector and angle of the space vector. Is it clear? For each switching state, how many switching states for two-level inverter? Hello, I want a response. How many switching states for two-level inverter?
8.
8 switching states. And so we are having how many space vectors for two-level inverter? How many voltage space vectors for two-level inverter? For each switching state, so for each switching state, we are having the specific values of VBO, VAO, VBO, VCO. And once we are in specific, we get a specific values of VAN, VBN, VCN for one switching state. Once we get for one switching state, VAN, VBN, VCN, we are having specific Vx and Vy. So for each switching state, we are having a specific value of space vector magnitude and theta. And two-level inverter is having how many switching state? 8 switching states. So how many voltage space vectors for two-level inverter? How many voltage space vectors for two-level inverter? Each switching state is having one voltage space vector. So 8 switching states, how many voltage space vectors?
8.
8 space vectors. And now it is possible we can find out the magnitude and angle of this. Can you do this exercise in home? You take one switching state. Let us we can go for this. Here, if you see it here, okay. Can you see which is our switching state we have given it here? Is it visible? Which switching state we have given it here? What is it visible? Switching state is visible. 1, 1, 0. This is our switching state. 1, 1, 0. Sorry, 1, 1, 0. What is meaning of 1, 1, 0? Which switches will be on? Anybody
1,
can
3 and
tell
2.
for 1, 1, 0, which switches will be on?
1, 3 and 2.
1, 3 and 2, correct. So the 3 switches will be on. And then what is value of VAO here? Now put the value of VAO. What is VAO?
VDC by 2.
VDC by 2. Similarly, what is VBO? Plus VDC by 2. Upper switch is on. And lower switch is on third. VCO will be a minus VDC by 2. Is it? This particular for this switching state. For this switching state, these are the values. Is it right? 110 for that. 1 means here VO is plus VDC by 2. VBO is again 1 means it is a plus VDC by 2. Okay, and 0 means VCO is minus VDC by 2. So is it clear? Depending on switching state. Now here we are having these values. VAO is already known. What is plus VDC by 2? VBO is plus VDC by 2. VCO is minus VDC by 2. Now what is our job? We compute VAN, VBN, VCN. Just use this matrix. VAO is known plus VDC by 2. So VAO is our plus VDC by 2. VBO is again plus VDC by 2. VCO is minus VDC by 2. 1 by third, 2 minus 1 minus 1, minus 1, 2, minus 1, minus 1, minus 2. This way are having a matrix. You get the AN, BN and CN. Just compute this, then AN will be 1/3 VDC. BN will be a 1/3 VDC. And CN will be minus 2/3 VDC. If we add these three, VAN plus VBN plus VCN, how much value we should get? If we add this VAN, okay, so we add the VAN plus VBN plus
0.
VCN. So we'll get the 0. This is a check. Okay. Can calculation you do it for any switching state, this addition will be 0. So if you just check putting the values VAO, VBO, CO, hurriedly while making calculation, we may make a mistake. Okay. And that can be verified with addition of these three voltages will be equal to 0. If it is not 0, you are not getting 0, means somewhere we made a mistake in the calculations. Somewhere you made the mistake in the calculations. You just check. So that will be one check. And once you are knowing VN is known, VBN is known, VCN is known. Now use the matrix what we are having Vx and Vy. Use this matrix. Use this matrix, whatever AN value is known, BN value is known, CN, it is in terms of VDC. Okay, so what is this? We are having VDC by 3, VDC by 3. And what is VDC? This is the input voltage given to the inverter. VDC is the DC link voltage. VDC is the DC link voltage given to the inverter. Once you know this, we get the Vx and Vy, and from that we compute the Vs and its angle. Now once we are knowing the VAN, VBN, VCN, particularly for 110, we obtain the Vx and Vy. So we have done it here. We obtain the Vx and Vy. So VAN, we put the values. I have not made it detailed calculation. VN will be VDC by 3, VBN will be VDC by 3, and VCN will be minus VDC by 3. And now putting this, our Vx will come as a plus 0.5 VDC. Vx will be coming as a plus 0.5 VDC and Vy will coming as a 0.866 VDC. So now, so our how will be our, we can just get it here. So this is our Vx is now a positive value. Is it right? This is a Vx, a 0.5 VDC. I will not write well. I'll just say it is a Vx. How much is the Vx is the positive value. And our Vy is also a positive value. It is a higher value. Okay, 90 degrees to this. And resultant of this is nothing but, this is the resultant, let us assume. Okay, this is our resultant. Okay, it is difficult to draw it, but okay. So this is our resultant we are having. And so both are positive. So angle will be in between 0 to 90. Angle will be, so 0.5 VDC square plus 0.866 VDC square. So and it comes as the VDC square root of this. So magnitude of space vector will be how much? VDC. Here magnitude of space vector is a particularly VDC is the magnitude of this space vector. VDC, this is our magnitude will be equal to VDC for this a particular space vector. And what is the angle, the theta? You find out this theta. Theta will be a tan inverse of
Vy
by Vx. And this angle will come out to be a theta here comes out to be a 60 degrees. Is it right? Theta will be come out as a 60 degrees. Is it clear? Theta will be so for this switching state, our space vector is having a magnitude will be equal to how much? VDC, and angle theta will be how much? A 60 degrees. And this exercise we have to repeat for how many switching states? 8 switching states, and we make the diagram of this. We make the space vector diagram. That all switching 8 switching states we make the diagram. And this is our diagram we have shown. What we have done the exercise. We have done 110. Is it right? We have done. This is a particularly we done this exercise. This is what we are having 110. Is it right? What we are getting, this angle will be equal to how much? 60 degrees. We get this will be a 60 degrees and magnitude will be equal to VDC. So this is one space vector we obtained. We done the exercise for this 110. Is it right? We have done the exercise for 110. You make a practice for all other 7. So we are having 8 switching states. Okay. So here we have written here 100. This is a V1 we can call 100. What is means? S1 is on, S6 and S2. Which devices are on for a V1 switching state? This is 100 switching state. In 100 means S1 is on.
Yes.
100 means S1 is on, S6 is on, and S2 is on. And for 110, we get our space vector will be magnitude will be equal to VDC. This and angle will be 0. You compute this. Similarly, you go for 010. 0 means S4, 1 means S3, again 0 means S2, S2, S3, S4, S2, S3, S4 are on. Then we get a space vector, how much it is, VDC magnitude, and how much the angle, 120 degrees. Similarly, you go for V4, a state, so 011. What is mean by 0? 4. 0 means 4, S4, and S3 and S5, 3, 4, 5. So when this is 011, we get a magnitude VDC, angle will be 180. Similarly, we are having 001. What is meaning of 001? 0 is 4, 6, and 5. 4, 5, 6 you can call it. We get a V5. And V6 means our 1 is S1, S6, and so here 101, 101. So here we get a 5, 6, 5, 6, and 1, or 1, 6, and 5. These are these. And here, if you put it upper 3 are on, what is switching state when upper 3 are on? When upper 3 are on, 111. Upper 3 are on, S1, S3, S5 are, we get 111. When lower 4 are on, we get 000. And for that you calculate, their value will comes out to be a 0. Their value will be a 0. And once they are getting the 0 value, the angle will also, these are two space vectors here. They are at the origin. 111 or 000. If you make it 111, what is the meaning of this? Load terminals are shorted. Is it right? ABC are shorted. Whether upper 3 are on or lower 3 are on, our ABC terminals will be shorted. And here our space vector is at the center. Its magnitude will be 0. So is it clear? The space vector diagram for two-level inverter. Is it clear? How to draw the space vector diagram for the two-level inverter? Now we have done 180 degrees mode of conduction. Yes or no? We are knowing now we are going for voltage source inverter, again two level inverter, bridge inverter. We are having 180 degrees mode of conduction. We are having 180 degrees mode of conduction. Yes, and here we have shown the switching signal. What is meaning of 180 degrees of mode of conduction? Each switch is on for how many duration?
180.
180 degrees mode of conduction. Each switch is on for 180 degrees. So here we are given just Q1 and Q4. Let us you assume S1 and S4. Okay. So Q1 is on for how much? 180 degrees. Q4 is on for 180 degrees, and then Q1. One switch from first leg Q1, Q4. So Q1 is on for 180, Q4 is on for 180 degrees. What is phase shift between first leg and second leg? Phase shift between first leg and second leg is how much degrees?
120.
120 degrees. So after Q1 or S1, our Q3 will up on by 120. Here each divisions are 60 degrees. Okay, we make divisions, vertical divisions. We are having horizontal divisions. We have made it, and this particular divisions we are having of 60 degrees. So after two divisions, 120 degrees, our Q3 will be on for 180 degrees. After that, Q3 will be off and Q6 will be on, and it will be like this. After Q3 on, our Q6 will be on, sorry, a Q5 will be on again after 120 degrees. So this is a Q5 on 180, then Q2 on for 180. And we have shown it here, which switch will be on. Here if you give first 60 degrees, Q1 is on, means it is first 1, 0, 1. So here, a particular for this case, what is our switching state? 1, 0, 1. Here second, Q1 is 1. Q6 means lower switch 0. Again Q2 is lower switch 0. So here switching state is 1, 0, 0. Here Q1 is on means 1. Q3 is on and Q2 is on means 0. So 1, 1, 0. Similarly here 0, 1, 0. Here 0, 1, 1. 0, 1, 1. Then here 0, 0, 1. Okay, and then again you can go on. So here how many switching states we obtain? In case of 180 degrees mode of conduction, how many switching states are possible? Huh? How many switching states are possible in case of 180 degrees mode of conduction? 6 switching states are possible. And which two switching states are absent?
000, 111.
Okay, 000 and 111, these switching states are absent. Okay, and why we are having a 6 state? Because it is having the 6 switching states in the particular this inverter. And two states which are absent, and this we have seen that 111, how much voltage it will give output voltage, and 000, how much is the output voltage? 0. Okay, so in case of particularly 180 degrees mode of conduction, these only 6 active states are there. So whatever we are calling these 6, V1, V2, V3, V4, V5, V6, these we can call as a active states, which is having a magnitude. Whereas 111 and 00, this we can call as a null states or inactive states. We can call as a inactive states because they will not give any output voltage. And our 6-step inverter is having all active states. Whereas this inactive states we can obtain in case of a PWM inverter, sinusoidal PWM or space vector PWM. We are having these two states. Null states are present in sinusoidal PWM or space vector PWM, but they are absent in 180 degrees mode of conduction. So who will give more output voltage? 180 degrees mode of conduction will give more output voltage, or PWM inverter will give more output voltage?
180.
180 because null states are absent. Null state is just time killing. Null states are just time killing. They are not giving any output. In PWM inverter or space vector PWM, these null states are present. So the output of sinusoidal PWM and space vector PWM is definitely less than 6-step inverter or less than 180 degrees mode of conduction. So is it clear? Today we discuss how to obtain the voltage space vector. What is the concept of voltage space vector and how to obtain it? Any questions? So
No
tomorrow
question.
at 10:15, is it convenient time? Tomorrow we have to conduct one extra lecture at 10:15 a.m.
Yes, sir.
Kumar, are you online?
Yes, sir. It is fine.
Okay, so tomorrow we conduct extra lecture at 10:15 a.m. Is it convenient to all? Is it convenient to all? Yes or
Yeah.
no?
Yes, yes, sir.
Yes, so we'll meet tomorrow at 10:15 a.m. Thank you.